Good morning, everybody. Professor Chung-Pei Ma is the Judith Chandler Webb Professor of Astronomy and Physics at UC Berkeley. She received both her undergraduate and PhD degrees in physics from MIT. Before joining the faculty of UC Berkeley in 2002, she was a postdoctoral fellow at California Institute of Technology and an assistant and associate professor at University of Pennsylvania, where she won the Lindbergh Award for distinguished teaching. She was the cosmology scientific editor for the Astrophysical Journal from 2007 for 10 years. One other thing I have to mention today is Professor Ma is an avid violin player. Now she won once the first prize winner in Taiwan National Violin Competition when she was young. And she was an exchange student at New England Conservatory of Music in Boston while studying at MIT. The topic Professor Ma has studied include the properties of dark matter and dark energy, the cosmic microwave background, gravitational lensing, galaxy formation and evolution, supermassive black holes, and the large-scale structure of the universe. She occasionally managed to climb out of the dark and lumpy universe. During these sunny moments, she enjoys conducting observation using telescope such as Keck and Gemini, right? That's her brain, right? Professor Ma has many academic achievements, which include member of American Academy of Arts and Sciences, Fellow of American Association for the Advancement of Science, member of Board on Physics and Astronomy, the National Academy of Sciences, Engineering and Medicine in U.S., member of Advisory Committee, Institute of Astrophysics and Astronomy, Academic Sinica, Taiwan, just to name a few. She has also won Maria Cooper Mayer Award and Annie Jump Cannon Award in Astronomy, American Astronomical Society in very young age. Having that said, we cannot wait to meet the talented lady astronomer, Professor Ma's work. Without further ado, let's welcome Professor Ma to give her talk on gravity's fatal attraction, black holes at the centers of galaxy. Professor Ma.
Okay, thank you very much. Let me try to share my screen now. Can you see the full screen? Okay, yeah, that's good. Okay, thank you very much for the invitation to speak at this new exciting series. I wish I were in Taipei and could be giving this in person. So I gathered that the previous few talks were on other kinds of exciting physics, and today I would like to bring you out of the Earth and fly towards the centers of the distant galaxies. In particular, I would like to talk about some recent excitement in black hole research. So just to start, I would like to sort of demystify black holes. Very often people think,黑洞是很可怕的东西, but actually 黑洞 are simple, really simple. They are predicted to exist by Einstein's general relativity, and it is a mathematical solution to his equation. And a black hole is completely specified by just three numbers: its mass, its spin, and its electric charge. And astrophysically, we usually think black holes will neutralize their charges. So really, what we are talking about is mass and its spin. So imagine, right, if all people can be specified by just three numbers, say your weight, your height, and your eye color. So two people with the same three numbers would be indistinguishable. It would be a very simple world. So this is the world that black holes live in. And as I will try to show you some data, interestingly, black hole, despite its mythical nature, or people think it's a very complicated thing to understand. In fact, black holes are sometimes the simplest explanation for many astrophysical observations. Okay, but what's difficult is black holes are black. They don't emit electromagnetic radiation by definition, so they are incredibly difficult to find. Okay. And there's basically just one number I would like to get across today that sort of sets the scale of black holes. So the critical number for a black hole is the size of the event horizon, basically this black disk you see in this image. Okay, and if you just use Newtonian 牛顿定律, some of you have learned, right, the escape velocity for say when you stand on a planet of mass m, and radius r is just given by square root of 2gm over r, where g is the gravitational constant. So if you set this velocity to c, the speed of light, and then rearrange this equation, you get the special radius called the Schwarzschild radius, and that is the radius of this event horizon within which even light cannot escape. And you can see that there's 2, there's g, there's c, these are all constants. So the key scaling here is that the bigger, the more massive a black hole is, the larger its event horizon. And the two numbers scale linearly. So you can put in the numbers, say you put the, the mass of the Earth, 地球的质量, if you put it in here, you put in the numbers, you can find that the Schwarzschild radius of the Earth mass black hole would be, a few centimeters, tiny. But if you scale up to the mass of the sun, this is a very important number to keep in mind, then the corresponding event horizon of a solar mass black hole will be just 3 kilometers. It's you can walk through that. Now, however, I will be speaking about some of the most massive black holes known in the universe, and these reach tens of billions of solar masses, the mass of the sun. We use the mass of sun as a unit to measure astronomical masses. So for a 10 billion solar mass black hole, the event horizon, as illustrated on this image, is about 5 times the size of the solar system, say out to the orbit of Pluto, just for the sake of, setting a scale. So it's large, but in the scale of an entire galaxy, the scale is still very small. So it's only the very central region of a galaxy would you be affected by the black hole. Okay. So I would like to before going to the big black holes, I would like to talk just briefly about the small black holes. And again, everything is astronomical here. So even by small, they are enormously massive. Okay, so it's all relative. And there are basically 2 types of astrophysical black holes, the small and the big. And briefly about the small ones, these are the end state of death of massive stars more massive than our sun. Our sun will not die as a black hole or as such a dramatic, will die as a white dwarf. But more massive stars are known to end their life spectacularly with a supernova explosion, and the center will collapse to a singularity, a black hole. So for a long time, the best known stellar mass black hole, these small black holes, is Cygnus X1. And here is an artist's impression of a black hole here, which we can't see. But the nature gave us a companion binary star, which is still on the main sequence, burning, fusing hydrogen at its center. So there's mass being dumped onto the black hole in the form of a disk, accretion disk. And this system emits copious X-rays and other electromagnetic radiations. So we can use the light to infer the mass of this black hole, thanks to its companion. And the mass for a long time was known to be about 15 solar masses. But interestingly, recently have been updated to 21.2 solar masses, not because of a better measurement of the mass, but because the distance to this system is measured better. And black hole mass requires determination of distance also, because we can only measure angular size on the sky. So to get a physical number, you need to get a distance at the same time. Okay, so the bottom line here is that these small black holes are on the order of tens of suns. And of course, the most exciting thing, in the past sort of 5 years, one of the most exciting things in astrophysics, in astronomy, in physics, is the discovery of the gravitational waves. And I'm sure many of you have heard about the LIGO results from 2015. Again, here in this case, they detected the gravitational waves from the merger of two black holes. So binary black holes that were bound in orbit, and at the final coalescence, you can see it formed a bigger black hole. And you can do the quick math. On the left-hand side, together is 65 solar masses. In the end, there was a 62 solar mass black hole. So energy better be conserved, MC squared should be conserved. So there's 3 solar masses of energy that was emitted in gravitational waves. And this is their famous plot. So now, 5-6 years later, many more such stellar mass binary black holes had been seen by LIGO. So now they can do statistics. Okay, so here, just look at the Y vertical axis. It tells you the system. So they are showing the 2 progenitors in each one and its final mass. Okay, and there are many and many of them known now, and they continue to discover more, and also black hole neutron star pairs and neutron star pairs. But again, just for the sake of today's talk, I just want to let you know that the masses, again, range from tens of solar masses to about 160 solar masses, right? It's very small compared to 10 billion that I will be talking about. So this is an extremely exciting frontier, and you are hearing, we're getting a lot of results in this part of the black hole study. Now, I would like to move on to the big black holes, the other type of astrophysical black holes. And here I will give you sort of 3 bigger and biggest black holes we know, and then I'll talk a little bit more about, do these big black holes come in twins also? And the answer is yes. And could we see the gravitational waves from these supermassive black holes? They haven't been seen yet, but they should be there. So to talk about these big supermassive black holes, we must start with the galactic center, the center of our own galaxy, the Milky Way. And this is the closest supermassive black hole we know, and this is the best studied. And in fact, it's studied so well that it won the Nobel Prize last fall. So unlike the stellar mass black holes I talked about, those were deaths of massive stars. So that's happening everywhere in the galaxy. Wherever you have massive stars, you will find those black holes. These supermassive black holes so far have only been found at the centers of galaxies. So this is the Kobe image of our own Milky Way's disk at the center here. And I'll also talk about M87, an enormous galaxy, the black hole at its center. Okay. And there are things called quasars, active galactic nuclei, and they're believed to be powered by supermassive black holes at the center too. So just very briefly, I would like to sort of summarize the incredible discovery made by Reinhard Genzel, who's my colleague here at UC Berkeley, and Andrea Ghez, for the discovery of a supermassive compact object at the center of our galaxy. And this story actually really started from in the late 1970s. And again, this is an infrared image of our own galaxy. We live sort of near the edge of the galaxy. So in fact, it's incredibly difficult to pierce through the dust, which scatters off optical light. So it's very obscure to look towards our own galactic center. It's very difficult to do. It's a little bit like, I like to use the analogy of a pizza. Imagine we are a little ant, 蚂蚁, right, or fly at the edge of a pizza. You're trying to look towards the center of pizza to decide, are we a pepperoni pizza? Are we a sausage pizza? Are we a mushroom pizza? It's actually in some ways harder to do than looking at a pizza that's external to us. So dust obscuration is one problem. The other is the galactic center. If you want to know where it is, go look for the Sagittarius constellation. I think that's called 人马座 or 射手座. Okay, if you may have the birth sign, astrological sign. So that's the direction of our own galactic center. And this is a beautiful image by the gravity team, Reinhard Genzel's team, showing you how many stars there are crowded at the center. Okay. And the key object here is a star, massive star called S2. So before talking about S2, I just want to give you a little bit of history of the study of our own galaxy center. It, in fact, started in the late 1970s, even before Reinhard Genzel showed up as a postdoc here at Berkeley. It was actually by Charlie Towns, Professor Towns at Berkeley. He won the Nobel Prize in the early days for an inventor of lasers and masers. But he became interested in the galactic center. And back then, there were only 3-meter telescopes on Lick right near San Jose here. So they were able to look towards the galactic center, Sagittarius A star. We know that because it emits a lot of radial and other kind of emission. And they use this very little by modern standard telescope and measure the velocity Doppler shifts of the ionized gas clouds at the central. You can see the scales here, right? This is the spar is 1.3 light years, 1.3 光年. So this is a pretty small region at the galactic center. And this plot is to show basically one side is being blue shifted, one side is being red shifted. So you can do a very simple back of the envelope estimate. And they already could tell that the mass enclosed within this volume is about 4 million solar masses. Okay, so what's the problem? What the problem is, are these 4 million solar masses concentrated at a point, or is it smeared out in this radius of 1.3, how many, about a few, about 1 parsec? You need to show that this mass is concentrated instead of being a bunch of, regular stuff, material within this volume. So the next 40 years, basically the effort is in zooming in as much as you can towards the center. And that required enormous advancement in instrumentation. Okay. So I just want to fast forward many years and come back to this special star S2. And this is really nature's gift to us, because this star that happens to be orbiting, and we can see it moving, has a period of 16 years, just short enough for astronomers to get our act together and to observe them. So this is one of the latest papers showing how so in already 2002, both teams were able to track this S2's movements. You can see this in some of the earlier data here. And the first paracentric approach, so it's when the S2 was closest to the galactic center, happened in 2002. But they couldn't get good enough data back then because this is pre-adaptive optics. So the disturbances of the atmosphere was too much for them to get very, very good data. But they already was able to infer the period of this star's orbit. So they had, and also 16 years to get ready. So in the meanwhile, huge advancement occurred, right? The Keck telescope came online, the very large telescopes came online in Chile, and adaptive optics, this special technique to correct the atmosphere's blurring in real time, was invented. So all these things came together to allow them in 2018 to even nail down the day of the closest approach of S2 towards the galactic center. And you can see they mapped this out over the few weeks. Okay, and the remarkable thing of S2 is when it's closest to this galactic center black hole, it's only 17 light hours away, right? Compare this to the few light years I talked about before. It's this incredible shrinking, zooming in, and getting both the velocities, radial velocities, and the proper motion, the position on the sky that allow them to reconstruct the mass of this object, of this black hole. And this is really a beautiful measurement that the black hole is about, with 3 decimal points, about 4 million solar masses. And at the same time, as I mentioned, they fit to the distance to the galactic center. So we also know very well now how far our sun is from the center of our galaxy. It's about 8.1 kiloparsecs, and 1 parsec is about 3 light years. Okay, so it's about 25,000 light years away from our galactic center. Okay, so that's the story of the supermassive black hole at the center of our own galaxy. And just remember this number, 4 million solar masses. And interestingly, among the supermassive black holes we know now, this is really on the small side. So I would like now to turn to a bigger black hole, and probably the second most studied black hole, supermassive black hole, is the one at the center of a giant external galaxy called Messier 87 M87. And M87 is a completely different galaxy from our Milky Way. It's about, just the galaxy itself is about 1,500 times more, the galaxy itself is many thousand times more massive than our Milky Way, and it's not a disk. It's shaped like an elliptical galaxy, so it's a different kind of galaxy. And it sits at the center of a city of galaxies called the Virgo Cluster. So these fuzzes, each one has probably trillions of solar masses of stars. This is a galaxy, that's a galaxy. And they are actually all at the same location, redshift distance. So we think they're gravitationally bound. It's called a galaxy cluster. Okay, and of course, this galaxy is now we've moved out by 2,000 times in distances. So it's about 54 million light years now. And the black hole is 1,500 times more massive. So we're talking about billions of solar masses. And this black hole, again, its existence had been inferred for about 40 years. And I just want to show you some pretty picture of M87 when you zoom in. It actually has a very famous jet, an ionized energetic plasma is being shot out from the center. We believe is being powered by the central black hole. And this is a Hubble beautiful image. Don't worry about the orientation. You can turn these pictures any way you like. But I just wanted to show that we actually were observing M87 using the Keck telescope, which the UCs we have access to. And I want to just show you, we were very excited when we pointed the telescope at M87. And this is even our guide camera. It's the little camera that on the guide camera, we're able to see the beautiful jet coming out. So it's, even though I've seen these pictures many times, it was quite exciting to see this when we actually looked at it ourselves. So this is just from my iPhone 7 that I should buy an iPhone 13 now, but that's my current phone. Yeah, this is a picture we took a year ago. Okay, so M87, again, I just want to go back to a little bit to the history. It had been known, inferred, about 5 billion solar masses using very early data, very similar to the galactic center. Again, it's not hard to get an enclosed mass. The question really is, how far in can you still keep this enclosed mass? Okay, so for about 34 years, M87 had been the most massive known black hole whose mass is directly dynamically measured. Okay, and this is a 1977 paper by Walt Sargent. And some of you have heard the very exciting result from a few years ago by the Event Horizon Telescope. So what they were able to do is to produce this first image using sub-millimeter interferometers to actually get this photon ring. Okay, for the purpose of this talk, I just want to highlight this equation that they are able, so this is a completely different technique. They are not using orbiting stars or gas to infer the mass, but rather they are using imaging, the size of this ring. And square root of 27 times, this is a black hole mass. So from that, they're able to obtain, again, about 6 billion solar masses for the black hole at the center of M87. Okay, and so that's what's happening right now. We are improving on the stellar dynamical measurements of the black hole, and I'm involved with the next generation EHT. We would like to perhaps go to space. It will be nice to observe other black holes. Okay, so that's all I want to say about M87 for now. And then now I would like to ask, right, we've talked about the galactic center, 4 million solar mass black hole, and the M87's 6 billion solar mass black hole. So is that it? Okay, so are there bigger black holes out there? So one very important relationship that astronomers had found in the past 2 decades was that the larger the black hole mass, okay, the larger its host mass, host galaxy's mass. Remember, these black holes all sit at the centers of galaxies, right? So we had seen the Milky Way. It's a very run-of-the-mill, normal, disky galaxy. M87 is much more massive. Right? The galaxy itself is much more massive, and the black hole is much more massive. And there are about 100 other systems that have been measured in between. It's very difficult to get the black hole mass to determine that. So there are so far about 100 that's directly dynamically measured. So we've been asking the question, is there anything beyond M87? And the expectation had been that yes, because M87, even though it's an enormous galaxy, is really not the biggest galaxy known. So there are bigger galaxies. So the question had been, do they host bigger black holes? And a lot of recent research in galaxy formation and cosmology had been asking questions like, how is this relation established? This is just a cartoon, but the data, show a lot of scatter, but there's an overall very tight correlation. It seems like the black hole at the center knows about its galaxy. So it's telling us that black holes and galaxy appear to grow symbiotically. So we want to understand how these black holes get to be of such enormous mass along the way as their host galaxies are growing. Okay, this is a very fundamental key question everyone is asking. So this kind of relationship offers a lot of insight for us. We can perform simulations to see if we can produce these relations in theory and to constrain a lot of models. Okay, so it's important to find out how many galaxies, to what extent this relationship go on to the high mass end. So, and this is where my work comes in a little bit, that my team has been doing this. I've been leading, I initiated the survey, massive survey that we study the 100 most massive galaxies measured by its stellar mass within about 300 million light years. So if you recall, Virgo M87 is at about 50 million light years. So we go much further out than Virgo. We actually go out to the Coma cluster and just have a systematic study of these galaxies and their central black holes. So it requires a lot of photometric and spectroscopic data, which I'll talk about momentarily. Okay, but let me just now highlight the 2 biggest black holes known that we were able to find first in 2011 and then in 2016, a different system. And just to contrast these 2 systems we found, okay, so I've put the 2 galaxies on the same scale here. So now you're seeing the Coma cluster. Okay, so it's yet another galaxy cluster. This one is a much more spectacular cluster compared to the Virgo cluster. It's much more massive. And you are seeing, it's very hard to portray that in these photos. These scales are just enormous, okay? And all these blobs you see here are member galaxies in this cluster. So Coma cluster really is the big city, the Shanghai of the universe. It's crowded with galaxies. And its biggest galaxy in this cluster is named NGC 4889. This is even bigger than M87. So we have known about these galaxies for many decades. But the question is, does it host a black hole at its center? And it had been very difficult to measure that. So we were able to do that in 2011. And the black hole came out to be, these 2 black holes are both in the range of 17 to 20 billion suns now. So you can see this is about 3 times more massive than the M87 black hole. And they are at much more distant galaxies. Okay, but one thing that was quite striking when in 2016, when we found a 17 billion solar mass black hole at the center of this much lesser known galaxy, NGC 1600, the surprise there was this group, no one had heard of it. Okay, NGC 1600 itself is a very massive galaxy, so it's in our massive survey, but it's not nearly as massive as 4889. And it sits in a group of galaxies. It's a small town. It's not the Coma cluster. Okay, it's like a small town of galaxies. But so we didn't quite expect to find a skyscraper in a small town, right? You go to Shanghai, you go to New York City, you go to Taipei, right? You got Taipei 101. You find the big skyscrapers, big black holes. You go to smaller towns, you don't expect to find a 100-floor skyscraper. So the question had been, how did this black hole get to be 7 billion solar masses? Somebody had to be feeding it over its cosmic time. Okay, and this environment is more starved of stuff, so it requires more effort to produce a black hole at the center. So a number of simulations, and I'm collaborating a number of teams to understand how you could form such a big black hole at the center of a pretty mediocre group, right? So the fact here I want to show is, even though these two black holes are of comparable masses, they live in very different environment, and that's a very important key diagnostic of how galaxies form, how black holes form. Any theory we produce, we must be able to explain both channels of growth. Okay, so I want to just spend a couple of minutes talking about why are big black holes hard to find. Right, we talked about how bigger black holes have bigger event horizons and they have bigger gravitational sphere of influence. So usually bigger things are easier to find, right? Small things usually are the hard ones to find. But in this case, it's really the distance that makes these things hard to find. And the reason is, in astronomy, usually the more massive something is, the more rare they are. We use the word mass function to capture the statistics of the mass distribution, of stars, of black holes, of galaxies. And all the mass functions fall with increasing mass, with different power laws, exponential form, whatever. But the bottom line is, the more massive you are, the more rare you are. So the volume density is lower. So in order to find the next biggest thing, you have to go further, right? Because they are rare. Like if you want to find a 7-foot tall person, it's unlikely to be in your lecture room, right? You probably have to go fairly far to find this rare person, right? Same here. So since big black holes live in big galaxies, and the Coma cluster, as I mentioned, is the most spectacular local cluster, we knew for a long time that we would want to go to the center of the Coma cluster. Okay, and the hard thing is really technically, observationally, how do you do that? And we need to, so in this case, unlike the galactic center where you can actually measure individual S2, these stars' orbits, when you go beyond our own galaxy, these things are just way too distant for us to resolve individual stars. Okay, so all we can get is sort of collective light, integrated light from stars. And we need to study these stars very close to the black hole, because only when you're very close to the black hole would their orbits would be the orbits be influenced by the black holes, right? If you're very far out in the galaxy, dark matter, other mass would dominate. So you wouldn't be sensitive to the black hole. So you need to get very close. And how close do we have to get? Well, for the Coma cluster, which is at about 330 million light years away, we need to be able to measure velocities of these stars, integrated light, okay, to within about 1,000 light years of the center. And just to put the scale, when 1,000 light years versus 330 million light years, we can do analogy. I'm now at Berkeley, so San Francisco is right across the bay. Imagine if I were standing here using a telescope. So this distance, if I shrink 330 million light years to the distance between San Francisco and Los Angeles, that 1,000 light years I have to resolve will be comparable to the size of Yo-Yo Ma Yo-Yo the show, right? So it will be like trying to measure how fast his fingers are moving if he were when he's performing in Disney Hall, say in Los Angeles, right? So this is pretty difficult to do, and that's what we have to do. Basically, sort of when you scale up the scales, and that requires biggest telescopes, best spectrographs, and so on and so forth. Okay, and so this is only one of the several reasons why these black holes are hard to study. Okay, but I just want to give you one reason. Okay, so again, the analogy here between the Milky Way, okay, S2 star, and these fuzz of stars we're seeing would be sort of like a swarm of bees. Okay, 蜜蜂, right? You see 很多蜜蜂在跑来跑去. So when this 蜜蜂, they're very close to us, like the galactic center, you can kind of see, right, each bee moving around. So you can try to measure its velocity. But when you put this swarm of bees very far away, you can see a fuzz, right? But you can't really resolve, our eyes cannot tell the individual bees apart, but you can still use a spectrograph to try to analyze the collective light from these bees and to get the velocity distribution of the bees. And that carries a lot of information about the central black hole. Okay, and that's the technique we're using to measure the black hole's mass, to discover and measure their masses outside of the Milky Way. For all the other supermassive black holes, this is the technique we're using. Okay, so again, I just want to show you, this is some of the things we use, like the Keck telescope. KCWI is a new so-called integral field spectrograph that allows us to get spectra of the entire field of view in 2D in one shot. We also use Gemini for some other galaxies, and we also need a space telescope to get our imaging data. And we also need to do a very extensive set of orbit calculation to model how stars orbit around black holes to tease out the black hole from our measurements. So we have many of these short orbit models running on supercomputers. Okay, so this is probably the most technical slide. I just want to show you, for those of you who do astronomy, in case you're curious about the spectra we see, I just want to give you an example of, this is the Keck KCWI from recent data we took. This is not M87, this is an even more distant, very faint galaxy. And this is the different field of view of the IFU. So the idea is, and Keck is such a large 10-meter telescope, it can collect a lot of photons from very faint objects. But we do have to look at it for exposed light. Our exposure times are hours for one position, okay? But just to show you, the central part of this camera plus the spectrograph gives us absorption line. So this is the spectrum now in the optical range, you can see in angstroms, from the stars in this elliptical galaxy for this one part. And the outer part, even though you can't see the light, it depends on the contrast on our screen, it gets much fainter, but we still can get incredibly beautiful absorption line features here. Okay, so for example, this is a very well-known calcium H and K lines, and this is due to the hydrogen beta transition. This is due to magnesium B. These are all very well-known absorption line features, and these are like fingerprints for a galaxy, DNAs. Okay, so so we use the broadening of these lines. So we fit templates. We have stars that have much narrow lines, okay, as template stars. And we ask, what is the velocity distribution for these blobs of stars that will produce a broadening of these otherwise very narrow stellar lines to this width, okay, to these broad absorption lines. So your black here shows the data, actual data that we reduced from the Keck to KCWI spectrograph, and the red line shows our actual fit. Okay, this is from, so in this fit, we can obtain the velocity distribution. So not just the radial velocity, not the velocity distribution, but we can get a skewness, kurtosis of the velocity distribution of the stars very close to the black hole. And these distributions carry all the information about the gravitational influence of the black holes on the stars. Okay, and then we compare with our numerical modeling to determine, right, a number of parameters. One of them is the black hole mass. Okay, so this is sort of the technique we use to discover a black hole. Okay, so I want to now just spend a few more minutes back to the question of, well, do big black holes come in twins? Okay, so I've shown you some examples, right? The galactic center, the M87, NGC 1600, 4889, these biggest black holes. I've spoken a little bit about how we study, how we actually find them. Okay, then we can come back to link up to the first question I asked, right? That stellar mass black holes come in binaries, as seen by LIGO. So do these massive black holes, can they be in twin in a binary system? And could they merge to form gravitational radiation waves, okay? So the answer is absolute yes, okay, that we know binary black holes should exist. And the reason here is different from the stellar black holes, okay? For stellar mass black hole binaries, we expect them to exist because, as you probably know, most stars exist in binaries. Our sun is more rare. In fact, it's a singlet. Most stars actually have a companion. So if you have two massive stars together, then they will both die as black holes, and then you will expect to see a stellar mass black hole. Okay, that's the small black holes. But for the massive black holes I'm talking about, the reason we expect to form binary big black holes is because they each live at the center of a galaxy, and galaxies merge, okay? And that's really the holy grail of the cold dark matter lambda cosmology that we know of today. This is how structures in the universe evolve. Okay, a primary channel for galaxies to grow, to get bigger, to get older, is through mergers and through gravitational pull, okay? And here, I'm just showing 6 beautiful pictures taken by the Hubble Space Telescope of 6 different systems, of binary systems. And galaxy mergers take millions, hundreds of millions of years to complete, so we can't hope to take pictures of that happening in real life, real time. But we could look at many, many systems and capture them in different stages of mergers. And this is an attempt to illustrate the increasing, advanced state of merger from 6 different completely unrelated systems. Okay, so this one, you can see 2 beautiful spiral galaxies. They're still somewhat apart, right? And the second system, you can now see the spiral arms being somewhat tidally distorted due to the gravitational interaction. And what you should keep in mind is this is the luminous part of galaxy. Each galaxy, we believe now, its mass actually is dominated by a dark matter halo, which has mass many more times of the luminous part. Okay, so there's a lot of gravitational force at work here. And here is another face-on example. And then when they merge, you can see the stars get scrambled, the gas triggers more star formation, and it's a complete mess. And it's a beautiful systems to look at, but they're quite rare because you got to capture them in action, right? And we can do numerical simulation, watching galaxies coming together. They usually pass each other a little bit and come in together, oscillate a few times, and they merge. And the key concept to have here is individually, if initially you have a supermassive black hole at the center, as the galaxies merge, the 2 supermassive black holes will come together to the center of the new galaxy to form a binary. That is energetically favored route because due to this thing called so-called dynamical friction. The 2 massive black holes will like to sink to the center of the new galaxy and form a bound object. That's pretty much given. That's a very natural channel, okay? And I just want to show you some more pictures. They're just remarkable systems, again, captured by HST. Okay, so here again, just picture that at the center of each galaxy, there is a supermassive black hole. And as the galaxies merge, we will get binary black holes. But the uncertain part of this picture is, will these binary black holes lose enough orbital angular momentum and energy to actually coalesce into a bigger black hole, and at the same time emitting gravitational waves. And there are various calculations showing yes, no, maybe so. And there are various reasons we may think they may get hung up. You have to lose enough orbital energy and momentum for them to merge. And it's the so-called last parsec problem. There are a lot of uncertainties. We think there are probably enough variables in this picture that will probably help. Gas will help them to merge. Triaxiality in the gravitational potential will help it to merge. There are various mechanisms that can overcome this possible hung up of the merger process. Okay, I just want to highlight this as an area of current research. But one can always ask, let's assume if they merge, how do we go about observing the gravitational waves? Okay, so here it brings me to sort of the final couple slides here. And this slide summarizes the gravitational wave spectrum, okay, as a function of frequency of the waves. And this H is the so-called strain value amplitude of the gravitational waves in this dimensionless number, predicted by general relativity. Don't worry about the actual definition. It's dimensionless. So the key is to notice how small these numbers are, right? These waves are very, very weak. And that's why it took incredibly sensitive interferometers of kilometers of length for LIGO to detect the signature I talked about at the beginning, right? And the key thing to note here is LIGO, these Earth-based interferometers, are only sensitive to waves, gravitational waves, at about 100 hertz. Okay, and again, remember, right, this is a completely new window into the universe. This is not electromagnetic waves, right? These are different kind of waves, gravitational waves. So let's step back and recall in astronomy how electromagnetic waves have given us so far all the information about the universe, right? You could plot in the x-axis here, could be the frequency of light, right? Then we have X-rays, we have, right, UV optical, gamma ray X-rays, UV optical, infrared, some millimeter all the way to radio, right? We have this entire electromagnetic spectrum mapped out over decades of studies. That's when you shake an electron, right? We all know when you shake an electron, it emits electromagnetic waves. Now, you shake a mass, you take a mass, you shake it, it emits gravitational waves. It's a completely different kind of waves. And LIGO only heard the highest pitch of this new orchestra, right? So I like to call these the piccolos, right? You may have heard the 交响乐团里面那个小的长笛. That's sort of the highest pitch one. And that's so far all we have heard from this new set of waves. There's this whole spectrum that's at lower frequencies that LIGO is not sensitive to, and you need other kind of detectors. And the sources are of increasingly higher and higher mass black hole binaries. So the ones I'm talking about, billions of solar masses, they are expected to emit gravitational waves upon merger at nanohertz frequencies. Okay, and there are some intermediate ranges, intermediate mass black hole, or slightly less, 10 to the 7 solar mass black holes coalescing will give out waves in this range. Okay, and this, of course, everyone is going into gravitational waves these days, and so two things maybe to pay attention to. One is the so-called LISA, space-based interferometers. It would be LIGO in space. So your baseline becomes much, much larger. And these are expected to probe sort of, 10 to the 7 solar mass black holes, or perhaps white dwarf binaries. Now, the ones I'm talking about, the waves are of such low frequencies that even LISA will not be able to detect. But we actually have been going on using a completely different set of detectors to search for these waves. And I'm a member of the NanoGraph, one of the pulsar timing array collaborations, the US-based one. And here the idea is not to use human-made instrumentation, but rather using nature as our detector. So I'll show you this slide to illustrate how we are using pulsars. These are rapidly rotating neutron stars in our galaxy. There are tens of them known. Okay, these are all radial pulsars. They've all found to pulse, and these are milliseconds. So every second, these neutron stars rotate hundreds of thousands of times, right? So, and pulsars are the most precise clocks known. The pulses are so precise that we can actually use the pulses as our detectors. Okay, and the idea here is we're on Earth, and there are these pulsars in our own galaxy, okay, Milky Way, populating our Milky Way. And externally, very far away, say M87 or some galaxies out there, at the center, if we have a pair of supermassive black holes I was speaking about, which formed due to galaxy mergers, if they can merge, then they will emit these nanohertz gravitational waves. They will come in, and these waves will produce minute, tiny fluctuations because they distort space-time in the arrival time of these pulsars. Okay, so we have a number of these mapped. This shows you, this is our galactic disk. These are some of the known millisecond pulsars. So we can correlate these arrival times of pulsars from different parts of sky and put limits right now and hopefully detect whether they're gravitational waves that's making the arrival time just show slight fluctuations. Okay, it's an incredibly difficult experiment. It's a high precision experiment because the strain, right, this distortion is about 10 to the minus 15. So it's a very small fluctuation. But what makes this feasible is that the pulsars are millisecond pulsars. So we have many cycles measured, right? So that increases your signal to noise. And also the pulsars themselves are very precise clocks. But of course, when we're trying to make such precise measurements, intrinsic noise from pulsars start to matter. Some pulsars show more so-called red noise due to perhaps earthquakes, neutron star quakes at the surface. So some pulsars are not as good clocks as others. So a lot of work is ongoing to analyze these pulses and to hopefully detect the gravitational waves here. Right now, what you see in the literature is all upper limits. But the upper limits are getting more and more stringent. And the prediction is in the next 5 years, hopefully, there's already tantalizing signs, but of course, we will love to make the first detection of nanohertz gravitational waves due to supermassive black holes. And the biggest black holes my team is finding have potential to be the hot spots for the nanograph and pulsar timing arrays, and that's my role in the collaboration. It's a collaboration of many hundred people. Okay, so yeah, I just want to conclude by showing you, just looking forward, that you could gather technology and new instrumentation are really the driving force of new discoveries in astronomy, probably other branches of physics too. And so I talked about pulsar timing arrays, LISAs, and at Berkeley, of course, UC, we are entangled in the 30-meter telescope saga at the Mauna Kea atop Hawaii. But there are 2 or 3 of these telescopes being proposed, being built, and this will provide us with even better angular resolution to find more distant black holes. And you probably know the next Hubble Space Telescope is called the James Webb Space Telescope, the next great observatory. This will be in the infrared. And I think the launch date was just pushed back by a few more months. It's supposed to be in October, next month. But the proposal cycle already happened, and my team was able to get Webb time to observe M87. So we are really looking forward to the launch of this telescope. Okay, so I want to just summarize by showing you some of the big questions we are asking in this community. How massive can black holes get? I mean, is 20 billion the maximum? We think it's getting close, but there is no theoretical a hardbound limit per se. Okay, but we know there will be fewer and fewer. So to quantify the volume density of these massive black holes is very important, and that's what we're working on. And we really want to know, how were they seeded initially? How did they form? And what had been feeding them to get to such an enormous mass, right? So mergers matter, gas accretion matters, and black holes have outsized impact on its host galaxy. So sort of the symbiotic relationship between the black hole at the center and their host galaxy is a very active research area. And we want to quantify them better. And I mentioned the environment, right? How come we are finding the big ones in big clusters as well as smaller groups? Okay. And of course, the binary picture of supermassive black holes. Can they merge? How many of them will merge? In what kind of galaxies? That's all the uncertainty in the current prediction for the pulsar timing array, the H strain level. How high the expected signal is depends a lot on how often they merge and how many of them are out there. That's why these measurements are these inputs are very important. Okay, and hopefully in the next few years, you will hear about the nanohertz gravitational wave discoveries. And just very last thing, okay, for the maybe high school students here and the general public is there had been, again, I want to debunk the myth, okay, that black holes are scary or they are. So one question I always get asked is, 我们的银河中间 right 就有一个很大的黑洞 are we going to get sucked in, right? Should we worry about falling into that black hole? Don't worry, we're at 25,000 light years away, okay? And far away from the hole, gravity is identical, okay? And that's why we need to zoom in to find the black hole. And to put it another way, 如果说我们今天这个太阳 okay, if you were able to just take the sun out and replace it, 放进一个 solar mass 的同样质量的一个黑洞, the Earth's orbit is not going to change. It's actually just going to keep going. But of course, it will be very cold and dark and it will die instantly. But just remember, black holes, their dynamical effect is limited to the very center. But they interact with the gas and they accelerate gas, and accelerating gas give out electromagnetic radiations and energy, X-rays, and those jets you saw. So black holes through the surrounding gas have enormous impact on the overall shape, color, star formation rate, all these properties of the host galaxy. So the black hole is a critical part of a galaxy, and galaxies are building blocks of the universe, and that's why it's so important to understand black holes. Okay, I think I'll stop here. Thank you.
Wow, thank you, Professor Ma, for showing us the depth and interesting aspect of the black hole study. And here you're talking about galaxy and black hole with the analogy of music, and that's amazing. For our audience, you can use the raise hand function to talk or write down your questions in the chat box. You can ask questions in either Chinese or English. 可以用中文问问题啊, Professor Ma understands it. Meanwhile, I'd like also invite Professor Ip, if you might, to join the discussion, since Professor Ip is also an expert in this field. At this time, in the chat box, we actually have an audience asking a question that has been asked in the university entrance exam this year. 就是今年的大考好像有一个问题哈，那我们先看一下这个聊天室的问题，那等一下我们再回到祁宏这边哈。这个大考中心的问题是这样，他说假设太阳系里面其他的天体依然存在， 但是太阳改成同质量的黑洞，那么对地球上的我们会有什么影响？尤其是对这个地球的降雨量跟潮汐会有什么影响？I think we'd like to listen here, Professor Ma's stand.
Oh, yeah, that's outside my study, right? So all I'm trying to say is the orbits will not change. Yeah, if you 问这个降雨量, oh, that's a very hard question. I'm sure, what is the correct answer? I think we're all going to die, so.
这是大考中心啊，就今年大学生就是要入学的考的题目，哇，真的是非常的困难。Professor 叶斌，你有没有答案？
我看那个应该是刚才那个马老师已经说了嘛，他说那个你看他最后一句话说 ，But it would be cold, right? It would be cold, and it would be cold.
It would be cold.
There's no radiation, and then so the Earth would be like an ice ball. I think that would be one part of it. Am I correct in saying that, Professor Ma?
Yeah, right away will be cold.
好，那我们接下来把时间给祁宏。祁宏呢，是我们在这个群体的有一位高中生，他非常的聪明啊，那对很多领域都颇有涉猎。我们听听祁宏有没有什么问题？祁宏，
现在林祁宏不是高中生嘞，他也是国中生嘞。
啊，真的啊，来，祁宏来。
好，谢谢老师。对，我是国中生，我今年是国2还国3？国3对，我是国3对。好，那So I have 2 questions. So first question is like teacher, so you have seen the speech inside say if the galaxies are growth on the merge, and when the 2 galaxies are merged and their black hole will also be merged. So the 2 black hole will be merged to the 1 black hole, and their massive will be bigger, and also they'll be produce gravitational wave. So my question is that because different kinds of the galaxies, they use different kind of orbits, different kind of speed to merge. And when they merge and something kind of black hole, maybe let's use the spiral track or high or ovals the orbit or a high or use very high speed or different kinds of orbit to merge. So my question is if the 2 different kind of black hole, let's use different kind of speed, different kind of orbits, different shaped orbits to merge, and can they to produce different shaped gravity wave? Like for example, in fairies, this gravitational wave, there should be the 1 circles, the spirals, the gravity wave. So if the 2 black holes they use very fast speed or oval orbits to through each other, how to say
Yes, I understand your question. Yes. So the answer is yes, actually, you can kind of like a LIGO team. Okay, so to get their numbers out, they made many calculations of the orbital angular momentum of the 2 black holes. Okay, another key ingredient is the spin of the black hole. Okay, which I mentioned at the very beginning. I didn't go into details. So that's the individual spin of the 2 black holes. So they don't have to be aligned. They could be anti-aligned. They could have different S. So it's kind of like quantum mechanics. You can have the LS coupling orbit, and different L orbital angular momentum and get different spins will produce different kind of waves. And for them, they do many parameter studies. For supermassive black holes, is probably less sensitive to that because everything is on a larger scale. But yes, we believe the supermassive black hole spins may have some memory of the spins of the host galaxy. That's actually one big question we are not quite sure about. So definitely the merger orbit of the galaxies may map.
Okay, thank you. So my second question is I have heard about something about the black hole knowledge in the few years ago in one speech inside. So let the speaker say, if the black hole their masses are bigger and their temperature will be lower. So my question is that possible? Because like teacher you said, something black hole their masses are very very big. So it's a lot of possible something very big, the massive the black hole. Their massive is to the one limit. So their temperature is absolute zero. So it's a lot of possible.
Right, so that's the so-called Hawking radiation, that the temperature, goes like inverse power, several powers of mass. So you don't need to worry about Hawking radiation for any of these astrophysical black holes, because the time scale for the temperature to change is much longer than the age of the universe. So Hawking radiation is only relevant for these. There's a third type of black holes I didn't talk about. They're called primordial black holes. And those are tiny, tiny things from, theory. None had been seen. And for those, you may have to worry about Hawking radiation. But for all the ones I'm talking about, that's really just not relevant at the time scale for us.
Okay, so also another short question is teacher, so you have to talking about the M187, this black holes, M87, yeah, this a black hole, and that's the image that also shows this the black hole, their size is 67 AU, and also it's one very big the photon ring, and the made by the many other come from the stars or from the other objects, their gas or the dust, something. So my question is, in the Earth, inside, if the night sky has the cloud, and this night will be warmer because the cloud they can keep in the heat. So it's also possible. So the same kinds, the effects are also appear in this kind of black hole. If the black holes, they have many dust cloud around there, and can this dust cloud to keep in the heat from this black hole into higher temperature?
It's a more complicated picture than just clouds and Earth, but definitely in the sense that the black holes both accrete gas and also imparts energy and momentum onto the surrounding gas. Okay, so it has a chance of actually shooting out gas through photon radiation even. Okay, so it's not just the temperature of the clouds, but even the momenta, the motion, and that's the word, we use the big word feedback. That's the buzzword feedback that everybody's studying in the galaxy formation world. So it's a more general picture than the cloud from, the analogy you're drawing, but it's similar in some ways. So that is, there is interaction between the black hole and the surrounding gas.
Okay,
but that's not going to impact the event horizon. That image you're seeing is due to the gravitational lensing of surrounding gas, and there's a lot of prediction based on GR, MHD, magnetohydrodynamics using general relativity. A lot of processing goes into interpreting that image. Read their paper 6. It takes 60 pages to explain that.
Okay, thank you, teacher.
Okay.
Thank you, Chi Hong, and thank you, Professor Ma. Professor Ip, do you have any questions or issues that you think is worth to bring out for our audience to discuss with
I
Professor
think it's
Ma?
one wonderful lecture, and thank you, Professor Ma, so much. Yeah, and she spoke in such a clear and simple way, and then unfortunately she had not brought into ballet dancing into her lecture.
Violin playing.
Right, and then yeah, of course, people are searching for the limit, of the mass of the black holes, and you just also brought up the issue about this Hawking radiation. So, what in your mind? What would be the lowest limit of the mass? Could there be such a thing, smallest black hole?
Yeah, so I think so there are sort of two regimes that are uncertain, right? So for the stellar mass people, as you well know, they are, I think, sort of arguing about whether it's 8 solar masses or 10 solar masses, right? So I think the question is, how massive does your progenitor, the actual star, have to be before they die as a black hole, right? The smaller ones will die as a neutron star. And a lot of the uncertainty is not in the original mass, but is mass loss phase, right? As the star is dying, it's losing a lot of mass. So that uncertainty, I think, is affecting the exact number. But I think, it's on the order of 8 to 10 solar masses. Okay, but another big uncertainty in the supermass black holes I was speaking about, which I sort of glossed over, is there are these so-called intermediate mass black holes, right? So the small black holes I talked about, 100 solar mass black holes, there are these millions to billions. There's this gap of a few thousands to hundreds of thousands solar masses. These are called intermediate mass black holes. There's no reason for them not to be there, but they should be at the centers of much smaller galaxies or perhaps globular clusters, compact star clusters. But we haven't been able to find any. And I think that's just because these objects are far enough, they're very close, but they're far enough that the black holes are so small, it's just observationally very hard to find. There have been a lot of reports of possible detections, but those were refuted later. It would be nice to understand this sort of desert right now.
Yeah, right. Okay, I think I have no more questions this time.
Thank you, Professor Ip. I think we have another audience. I'd like to take the last question. Mr. Hong Yutang. Hong Yutang, as I know, should be from the Air Force Academy. Mr. Hong, what's your question?
We cannot hear you.
Mr. Hong? Mr. Hong, are you there?
He raised his hand, but then
yes,
no sound. I think
but then maybe we'll ask his question in text and after the meeting today. I'd like to close down today for our great discussion. I think it's a great day in the vacation days of Moon Festival to look at the sky. And if you want to know more about black hole and you want to hear how Professor Ma played the violin, you can look at the program produced by Nova, I believe. It's called Black Hole Hunter. I have seen the video of Professor Ma playing violin in the program, so it's great. It's astonishing. There are a lot more to talk about, and I think we should arrange another section in the next season to invite Professor Ma again. If Professor Ma comes back to Taiwan anytime, please make sure you visit us in Central University. And before we meet, thank you. You have to. Before we meet again, I believe we can contact Professor Ma for further questions in private. And thank you very much again, Professor Ma, for sharing with us today.
Thank you very much for the invitation. It was a pleasure.
Thank you. Thank you very much. And next month, we will invite Professor Chen Muqing, Professor of Physics and Astronomy, School of Physical Science, University of California, Irvine, to give us a talk. And thank you, everybody, for participating in our event today. See you next time and have a very good Moon Festival vacation. Thank you, Professor Ma.
Okay,
thank you, everybody.